All right, so this is the first video of chapter 7. Why don't you pause, copy this panel down, press play. So in chapter 7, we're going to really get into confidence intervals, and we're going to look at a variety of scenarios where we can calculate these confidence intervals. So in section 7.1, we're going to look at calculating confidence intervals when our data is coming from normally distributed, okay? And what we're going to try and do is we're going to try and seek a confidence interval for the population mean mu. So we're going to have an estimator for mu, and then we're going to use that to calculate a confidence interval for the population mean mu. And we got 3 scenarios. The first and easiest is where we know the standard deviation or the variance sigma. The second is where we don't. And the third is where we have 2 sets of data from 2 different normally distributed data sets. And we're looking for a confidence interval for the difference of the population means, okay? All right, so let's look at the first one. And we actually already know how to do this one, but we're going to run through an example to make sure it makes sense. So we got data coming from a normal distribution, and we happen to know sigma, the standard deviation. And we don't know mu, but we're going to use an estimator mu to develop a confidence interval for it, okay? All right, so why don't you pause, copy this panel down. So we're going to explain this scenario via an example. So we've got the Center of Disease Control, the CDC, has determined the weights of 13-year-old girls is normally distributed with a standard deviation of 24.6 pounds, okay? Now, we then grab a data set. We grab the weights of 150 13-year-old girls. And, you know, Excel or R tells us that the sample average is 98 pounds. We'd like to use this data to get a 95% confidence interval from mu, okay? Well, we're going to unsurprisingly use the sample mean as the estimator of the population mean. After all, we have it, and it's unbiased. So yeah, it's a good one. And if you recall from the various times we've done this computation, the variance of the sample mean is 1 over the number in the sample times the variance of each one of them, okay? We've done that calculation repeatedly. So in our case, that would be 1 over 150 times 24.6 squared, since we knew sigma was 24.6. Or in other words, the standard deviation of x bar is 24.6 over the root of 150, okay? Now, in particular, that means that we know, well, so by the way, since x sub i's are normally distributed, so is the sum of the x sub i's and a constant multiple of the x sub i's. So x bar is normally distributed, okay? That was one of the results of x1 up through xn being independent and identically distributed in a normal distribution. Their sum, their difference, constant multiple of them is still normally distributed. It's not the central limit theorem because we knew each of the xi's was normal to begin with, all right? Okay, well, anyway, that means x bar is normally distributed, and I know its mean is mu, and I know its standard deviation, so I can standardize x bar minus the population mean, which I don't know, divided by its standard deviation is standard normal, okay? And then since I'm after a 95% confidence interval, please observe on the table for the N01 is that at 1.96, I have 97.5% of the area to the left of 1.96, which means 95% of my area or my probability is between 1.96 and negative 1.96. So 95% of the probability for standard normal is between negative and positive 1.96. I know my x bar minus mu over 24.6 over root 150 is standard normal, so I can replace z with that. And now I'm simply going to go through and solve for mu carefully. So the first thing I'm going to do is take this fraction 24.6 over the root of 150 and multiply it to all 3 sides. There it is, okay? I'm then going to subtract x bar from all 3 zones. So I have my minus x bar and my minus x bar. My x bar is canceled. And here's the tricky bit. I'm now going to multiply all 3 pieces by -1. So that's going to flip all my inequalities. So this guy, when I multiply it by -1, is going to go over to here. So -1 times negative x bar gives me the positive x bar. -1 times this fraction gives me the negative of the fraction. -1 times mu is mu. -1 times this is going to come over here. So -1 times the negative x bar is my x bar. And -1 times this negative fraction gives me the positive fraction. Okay. All right. Well, so great. 95% of the probability is between this value and this value for mu. So that's my 95% confidence interval. And if I replace x bar with 150 and grind that out, I get the interval 94.06 to 101.94. So nothing new. I mean, everything we could have done in Math 313 just apply to a specific area. So there's my 95% confidence interval for the population mean mu. All right. A couple of algebraic steps are quite challenging. Please let me know in class if you're having trouble figuring out exactly how I'm doing that. I can run through another one. One more panel. Okay, so you copy, pause, copy, and then play. All right, so continue with the example that we just finished over there. What we say is that we are 95% confident that the population mean weight of 13-year-old girls is between 94.06 and 101.94 pounds. That's what we say. What this actually means, though, and I don't know, gold star here or red stars here, this is important. What we actually mean, though, is if we take many, many random samples of 150 13-year-old girls' weights, if I have a bunch of these 150 item random samples, and if I form 95% confidence intervals for each one of them, then 95% of these confidence intervals will contain the true population mean. Okay, so if I simulate this process 1,000 times, generating 1,000 95% confidence intervals, then I'm pretty sure that 950 of those confidence intervals will contain the true population. Okay, all right, so that's an important statement to lock into your brain. All right, now in summary, what we just did is we had some data from normal distribution where I knew sigma, and I was calculating a 1 minus alpha times 100% confidence interval for mu. And what I did was I took the sample mean, subtracted or added some quantile times sigma over root n, okay? And Q was the 1 minus alpha over 2 quantile of n01. So in the last example, I wanted a 95% confidence interval. So my alpha was 5%. And 1 minus 5% over 2 is 1 minus 2.5%. So that's a 97.5% quantile. So that's why I used that 1.96, because it had 97.5% of the area or the probability to the left of it, right? Oftentimes we replace the Q with Z for standard normal, alpha over 2, denoting half of the alpha that you're provided. So in our case, this would be 2.5. Okay. All right, one last quick example here. We're given some data, 2.8, 3.2, 3.6, 4, 4.8, 5.1, and we're told it's drawn from a normal distribution. We don't know the mean, but we do know sigma, the standard deviation, is 3, and I'd like an 80% confidence interval from you. All right, well, sample mean, easy to calculate. Add up the data, divide by the number in the data, which is 6, and I get a sample mean of 3.92. I want an 80% confidence interval, so my alpha is 0.2. So I'm going to take half of that, 0.1, and I want 0.1 of the area to be on either side of the confidence interval. So Z.1 is Z of 90%. So from the table, if you look up the 90% spot, you get 1.282, or you could use R. So using the summary up here, X bar minus Z.1, 1.282 times 3, which is sigma, divided by the square root of n, and then plus that same exact quantity as my 80% confidence interval, and I get 2.35 to 5.49. Okay. Now, the quantile times sigma over root n is called the margin of error of the confidence interval. It's how far from the sample mean to the left or to the right we move to create a confidence interval. So that's called the margin of error. All right. Let's see, is that gonna calm down? I never know about the lighting here. All right, hopefully. Zoom out. Oh, look at that. Okay, maybe now you can pause and copy if you didn't before. Okay, that's the end of this video.